Hello. So today we will start with the example of a overdamped pendulum. So as I was explaining in the previous class, overdamped pendulum looks something like this. You have the support here and you have the beam from which the pendulum is hanging like this. This vertical direction, we call the angle with respect to the vertical as theta. And suppose there is a torque which is applied in this direction, which we call gamma, and the pendulum oscillates around like that. So it's like this. And then it tries to come back to its initial position. Okay, so suppose that the weight of the pendulum is the mass into gravity, and the length of the beam is L from which the pendulum is hanging. Then the equation for the change of rate of change of angle theta of the double pendulum is given as ml square theta double dot plus d theta plus m g theta equals gamma. So this is the uh, force balance equation for the pendulum, where the parameter small v, it's the viscous damping due to the friction. So therefore, it is proportional to the velocity of the pendulum. All right. Now, this can be broken down into two differential equations, which gives us a second order system. So in order to make the approximation of a first order system, what we consider is that this term is negligible. That means the acceleration of the mass is negligible, and this will happen only when the damping term is stronger than the acceleration term in the force balance equation. So when that happens, then the equation turns out to be d theta dot plus mgl sine theta is equal to gamma. Now this is a first order equation in the variable theta. So this is basically like the flow on a circle, which we had seen in the previous lecture. Now the next task is to non-dimensionalize this equation. So what we do is that we divide both sides by mgl sine theta equal to gamma by mgl. Okay, so we let tau equal to mgl by t into t as some non-dimensional time scale, and we define the non-dimensional external torque as gamma by mg. So you see this non-dimensional external torque, it is nothing but the ratio of the applied torque to the torque due to the weight of the resisting torque due to the weight of the pendulum. So then with these quantities, the dynamical equation becomes d theta d tau is equal to gamma minus sine theta. So this is the equation we now have to solve in order to study the dynamics of the overdamped pendulum. So there can be two fixed points or no fixed points depending upon the value of the parameter gamma. So for the fixed point of this equation can exist only when gamma is equal to sine theta star. Now for this equation to hold, we should have mod gamma should be less than 1. Otherwise, mod gamma is greater than 1, then there will be no fixed points and the pendulum will keep on oscillating back and forever. That means, so in the oscillation case, we can map this onto an interval like this. So this is the case when gamma is greater than 1. So this is the fast part of the oscillation, and this is the slow part. So the oscillation is fast when the pendulum is at the bottommost position and slow when it is at the topmost position. So slow when it's on the right hand side, it's pi by 2, and fast right hand side minus pi by 2. So pi by 2 would be somewhere over here. This portion is minus pi by 2. So the oscillation of the mass is fastest over here and slowest on the other side. Now, when gamma equal to 1, then this curve just about intersects these x-axis like this. There's a point of intersection over here, and there is a fixed point. And the flow is slow in this direction. So this fixed point is stable from the left. Right. So what this means is that if and the fixed point corresponds to pi theta equal to pi by 2. So suppose the mass is over here and it is supposed to go in a circle like that. So if the mass starts somewhere from here, it will go up like this and stay at pi by 2. But if the mass starts just above pi by 2, then it will go all the way around the circle and then come to this position. And now, when gamma exceeds 1, then what happens is that there is one fixed point over here and one fixed point over here. So this becomes a stable fixed point, and this is the other one is the unstable fixed point. So on the circle, it will look somewhat like this. So this is the circle, then one fixed point will be over here, which is the unstable one. The stable fixed point will be over here. And corresponds to theta star. So the flow will always be directed towards this fixed point. Regardless of where we start from, the mass will come and become stationary at this fixed point. So this is what an overdamped pendulum looks like. So if you try to understand the physics of the problem, it basically means that when gamma becomes less than 1, in other words, if the external torque is lesser than the torque due to the inertia of the mass, then the mass will hang somewhere between pi by 2 and 0 in a stationary state. On the other hand, if the external torque exceeds the torque due to the inertia of the mass, then it will oscillate round and round in the circle. And finally, when gamma is equal to 0, we see that the stable fixed point goes to theta star equal to 0, and the unstable fixed point goes to the top at theta star equal to pi. All right, so that means there is no external torque. The pendulum will be hanging vertically. So now we can take a look at a problem on this overtime pendulum. So the problem is as follows. Now suppose the overtime pendulum is connected to a torsional spring. Okay, what do I mean? A torsional spring. So you have the pendulum like this, and there is a spring like that. So this thing is a spring, okay, and this is the angle theta. So suppose there is a spring which goes around the circle in this manner, with which the overtime pendulum is connected, right? So because it is connected to a spring, it will always have a restoring torque acting on it if you try to displace it slightly. And this opposing torque, it is proportional to the angle which it makes with the vertical. So therefore, it is proportional to this term. Theta. This is the cosine q to the spring. So then the equation of motion in the first order approximation becomes v theta dot plus TL gamma minus the opposing dot, which is k theta. So the first thing that we have to do is to normalize the equation. So again, we do the same thing. We divide both sides by mgl sine mgl. So let us suppose that we keep define tau and gamma as earlier, and you define capital K as small k by GL, then the equation becomes by tau is equal to gamma minus k theta minus sine theta. So the first thing that we ask is that, does this give us a well-defined vector field on the circle? So we had seen previously that in order to give a well-defined vector field on the circle, the velocity at the same point should be the same. Now theta equal to 2, 0 and theta equal to 2 pi. Both are the same points on the circle. But on these points, the velocity of the pendulum is gamma and gamma minus 2 pi k. Now clearly, k is not equal to 0, right? So the velocities at the 2 points are different. So this violates the uniqueness theorem. Therefore, this velocity field is not, vector field is in fact not well defined on the circle. Now, if you try to see what the pendulum does in the long run at long times, then basically because of this minus k theta term, the oscillations will damp out and will try to come back to its original position because there will be an exponential damping of theta with respect to time. Okay, so this is how you can analyze a system such as this one. So now we can move on to another example of a flow on a circle. And this one is an example of a biological system. And this system is nothing but fireflies. So one must have seen at in the evenings, the fireflies come out and they start flashing and different manners. Right. So one thing which has been observed quite commonly is that when there is a huge bunch of fireflies flashing together, something which has been commonly observed is that when there is a large number of fireflies which flash together in unison, then what happens is that the different fireflies, they try to synchronize their frequencies with each other. Okay, so basically, if one is lagging in phase with respect to the other firefly, then the firefly tries to increase its frequency or increase its rate of flashing so that it can come into phase with the other firefly. Similarly, if the one firefly is moving ahead in phase, then it will try to slow down its rate of flashing so that it can again come in phase with its partner. So this is how fireflies try to end up synchronizing with each other. Hello. Okay. Yeah. So there was an issue with the internet. So as I was saying, the flashing rhythm of fireflies has been puzzling ecologists and biologists for a very long time. It was only in the 1970s that the flashing of fireflies was studied from the point of view of a dynamical system. So one experiment which was conducted was that suppose you have a firefly and it is flashing around like this, and you bring a torchlight near it. So this is the torch. This is just a schematic diagram, and the torch is emitting flashes, and there is a certain frequency at which at with which it emits its flashes. Okay. So what is done is that the torch is periodically turned on and turned off in intervals of time, which one can say t. And it was observed that regardless of the natural rhythm of the flashing of the firefly, it tried to synchronize with the torch. So when and it was found that if the flashing of the torch was slow, then the firefly was able to synchronize with it. However, if the frequency of the flashes of the torch was increased beyond a certain critical value, then the firefly was no longer able to entwine with the torch. Okay, so this form of synchronization is also known by this term called entrainment. So if the torch flashlights starts blinking very fast, then the firefly is unable to entwine its rhythm with that of the flash. And then what happens is that as the firefly tries to catch up with the torch, initially when it is falling behind, it tries to speed up, but it's unable to catch the torch. So the flashing of the torch, it somehow laps the fireflies. Like we had seen in the previous class, the example of a fast runner lapping a slow runner. So the flashing of the torch somehow laps the flashing of the fireflies. And then once it gets lapped over, again it tries to synchronize with the torch, but it fails to do so. So there is a continuous phase drift between the firefly and the torch beyond a certain critical frequency of flashing, but below that critical frequency, they tend to synchronize. So the next question which was asked was that can we build a mathematical model for this? So suppose we denote this variable theta as a function of time as the phase of the fireflies flashing rhythm. Okay. Now, in the absence of any external stimulus, it will simply flash at its own natural frequency, which we call omega. It's a natural of the particle. So, in the absence of this stimulus, theta dot as a function of t will be omega. So the firefly happily flashes at its own natural rhythm. Now, suppose there is an external periodic stimulus. We call the phase of the external stimulus as psi of t. Okay, so this is the phase of stimulus. This stimulus can be a flashing of the firefly, another firefly nearby, or it can be an external light source also. And suppose omega is the natural frequency of the stimulus. Okay. Then the dynamical equation for the flashing of the stimulus is nothing but psi dot as a function of t is equal to capital omega. Now, in our explanation, we had seen that the firefly tries to catch up with the stimulus. In other words, it tries to minimize its own phase difference with respect to the stimulus. Right. So when the stimulus comes in, the equation for the evolution of the phase of the firefly will change, and a simple model which can model this is as follows. Beta dot is the natural frequency omega plus a sine psi minus theta. So what this extra term does is that if psi is greater than theta, that means if the stimulus is ahead in phase of the firefly, then this term it becomes greater than omega. So the flashing frequency of the firefly increases as it tries to come into phase with the stimulus which is ahead of it. On the other hand, if psi is behind theta, then the right hand side is less than omega. In that case, the firefly tries to slow down so that it comes in phase with the stimulus. And the parameter capital A, it tells us how quickly a firefly can come into sync with its external stimulus. So if A is large, then the speeding up or the slowing down of the firefly, that means the adjustment of its phase happens over a smaller time scale. So we call A as the resetting strength of the firefly. Okay, so now let us analyze this dynamical model. So now we are trying to see whether the firefly can synchronize with the stimulus or not. So to measure this kind of synchronization, which in common literature is also called phase synchronization. There can be different kinds of synchronization. This is one very specialized case, which is called phase synchronization. So phase synchronization can occur if the phase difference between the two systems, in this case the firefly and the stimulus, becomes a constant value. It need not necessarily be zero, but it can come down to a constant value. Okay, so for this, we need to study the phase difference of the system. So the phase difference is defined as phi, which is theta minus psi. This is the and the rate at which this changes is nothing but theta dot minus psi dot, or in other words, y dt is equal to right. So this equation for the phase difference simply follows from this equation. We call this equation 2, equation 1. Now what we do is that we try to non-dimensionalize this equation as we had done earlier. So we divide both sides of the equation by capital A. So we denote the first term on the right hand side as mu. So this can be seen as a measure of the frequency difference with respect to the relative resetting strength. Now this is more useful than the parameters we were observing earlier, because we saw that the ability to synchronize depends upon two things. One is the difference between the natural frequencies, and the other is the resetting strength. So this parameter gives us a combined effect of the two. So this tells us that mu will be small if the resetting strength is very large, or if the difference between the frequency is small, even if capital A is small. And mu is large if either capital A is very small or the difference between the two frequencies is large. Okay. And we can also define a non-dimensional time scale as tau equal to AT. So again, when the resetting strength is small, the tau is again small and it can be seen as a relaxation time. So then we have I tau is equal to mu minus sine phi. So this is the dynamical equation which we must solve. So as previously, there can be three different cases. One is mu greater than 0, mu equal to 0, and mu less than 0. Beg your pardon. Um, this will be there are actually 0 less than mu less than 1, mu equal to 1, and mu greater than 1. So in the first case, the graph of the right hand side with respect to phi is like this. So here there is a fixed point over here, which is a stable fixed point and unstable fixed point. So the flow is towards this fixed point. So you see the when mu is lying between 0 and 1, there exists a stable fixed point in phi. That means the phi tends to a constant value. So there will be phase synchronization between the stimulus and the firefly when this parameter mu lies between 0 and 1. So we can say that phase synchronization exists here. Similarly, when mu is equal to 1, then it becomes. So there is a half stable fixed point over here. It's approached from the left hand side and goes like this. So again, uh, there can be a synchronization over here in this borderline case also. And when mu is greater than 1, then there is no intersection between this curve and the x-axis. So there is no synchronization, and the phase difference between the firefly and the stimulus drifts continuously. So here, no phase sync, only phase drift. So you see, with this simple model, we have been able to understand how phase synchronization can occur between a firefly and its stimulus, and in which situations such phase synchronization cannot occur. And you see that if you decrease, suppose you decrease the frequency of the flashing of the firefly, because the resetting strength, capital A, it is a property of the firefly by itself. It differs from one species to another. So what is in our hands is the external stimulus over here. So if you decrease the frequency of the external stimulus, that means if you control capital omega from a large value to a small value, there is initially no phase synchronization, and after that there is a saddle node bifurcation, and then two fixed points get formed in the space of pi, and then you get phase synchronization. Now, an interesting thing which one can study over here is the range of synchronization. Okay, so the condition for synchronization is that 0 less than equal to mu less than equal to 1. And we saw this basically means right. So this is the or better condition is that the magnitude of this parameter should be less than 1, right? Because these two fixed the necessary condition for the existence of synchronization is that the two fixed points should exist. And this is satisfied only when this condition is satisfied. Or in other words, this basically implies that the external driving frequency, capital omega, it should essentially lie in this parameter range. So this is the condition for, so if omega, capital omega satisfies this condition, only then will we have synchronization between the firefly and the external frequency. So one can draw a graph of omega versus small omega versus A. So you have the resetting strength in this direction and omega in this direction. Okay, so this corresponds to the point A equal to 0. So if the resetting strength is 0, then okay, so this is omega equal to omega and A equal to 0. So you see if the resetting strength is 0, then there will be synchronization only if the external frequency capital omega is equal to small omega. Now, if you increase the value of A, you see that you get these two lines like this. So this line is basically this. This is the omega minus A line, and this is the omega plus A line. And in this entire region, you get the synchronization. Okay. So this basically means that if you increase the resetting strength, there is a large range of frequencies. That means there is a large range of capital omega across which you can get the synchronized behavior. So this will be capital omega. So this basically denotes the region of synchronization. And this is what is known as Arnold term. So this was first observed by this researcher when he was studying the phase synchronization of chaotic systems. So you see a sort of an Arnold term for this linear system as well, which basically gives us the regime of synchronization. Now, when there is no synchronization, you can also find out the period of drift or the beat frequency between the beat period between the firefly and the external stimulus, which one can say as TD, that is integral dt. It's nothing but T2 by T5, which is equal to from 0 to 2 pi. This was the right hand side, which we had earlier. So again, if you solve this equation, it turns out to be 2 pi by square root of square minus x square. So you see when the frequency difference approaches the A, then when frequency difference approaches A, then the phase drift basically slows down at a point, and basically the phase drift slows down where the synchronization, where the fixed point just tries to form. So this basically means that the fireflies comes very close to synchronizing with its external stimulus, but it's still unable to do so, and as the stimulus moves ahead in phase. Like we had seen earlier for the critical slowing down of the overdamped pendulum and also the non-uniform oscillator. So one thing is that here we had assumed a form of a system where the right hand side, the non-uniformity in the right hand side, that means the resetting stuff, it was given by a sine function. Now, instead of a sine function, one can also have other periodic functions on the right hand side, as it can vary from one species of firefly to another. So suppose you have a triangular wave sort of a function, okay, which looks like this instead of the sine function. So we can call this as f of phi as a function of the phi I by and so on. So you can have something which looks like this. So then the equation for the phase difference of the firefly would then become or instead of t, we can simply take it as a tau for convenience, assuming that we have normalized this time by the resetting parameter into minus f of phi, where f of phi is basically this function. So basically here we have replaced this sine phi by f of phi. Now we can again do the same analysis which we had done earlier. So when so the peaks of the function, they occur at pi by 2 and the troughs occur at minus pi by 2. Okay, now if you are to draw this function, then you will see that for values of mu which lie between 0 less than mu less than pi by 2, what happens is that right. So there are again two fixed points like this where this is the origin. So this is the RHS basically as a function of pi. So you see that there exists a fixed point for this phase difference when mu is between 0 and pi by 2. And this fixed point basically implies that there is phase synchronization in this regime of values of mu. And when mu is greater than pi by 2, then simply the wave looks like this, and there are no fixed points here. Yeah, so the screen broadcast had stopped in between. So this is what happens for mu between 0 and pi by 2. There are two fixed points. So there is synchronization, and when mu exceeds pi by 2, there is no synchronization, and there is simply a phase drift due to the absence of fixed points. Okay, so the range of entrainment is therefore this. So you see that for different kinds of periodic waveforms, you can have different ranges of entrainment depending upon the amplitudes of the periodic waveforms themselves and also their frequencies. Okay. And the transition from synchronization to desynchronization can happen in different manners. For example, previously we had seen that the fixed points they follow this square root law because of a saddle node bifurcation. However, here the square root law won't be there because there are straight line segments in this triangular waveform, and therefore the approach to phase synchronization will be a linear approach rather than a square root approach. Okay, so there can be subtle differences depending on the nature of the waveform. So these are two examples that we have covered till now. Also, other examples can exist, like for other systems are there which can be defined in terms of flows on a circle. For example, one can also define these excitable systems like neurons as a flow on a circle, right? Because excitable neurons follow this slow fast time scales. So basically, you had seen this critical slowing down, which happens when the fixed point just about forms. Then, if you start from one side of the fixed point, complete one and complete you complete one whole excursion of the circle and then come back to your initial position. So that can be roughly mapped onto the release of an action potential by a biological neuron. So in excitable systems like neurons can also be mapped to flows on a circle, which we will see probably in the upcoming classes. But for the moment, we conclude our discussion on one-dimensional systems and flows on circles, and now we move on to 2D flows. So 2D flows are much more complicated than one-dimensional flows because the phase space manifold is no longer one-dimensional, it becomes a two-dimensional manifold. Okay, so the first thing that one tries to study over here, we will start with is linear system. We will gradually move into nonlinear systems, but first it makes sense to analyze linear systems because again, when we do nonlinear systems, we will be doing stability analysis where we have to linearize the system again. So I'll take a break for 5 minutes. After that, we'll be back with this study. Okay, coming back to our discussion on linear systems and how to analyze their stability. So, by a two-dimensional system, I mean that the system has a two-dimensional space. So, suppose you have a dynamical system consisting of two variables, x as a function of t and y as a function of t. Then the phase space of the two-dimensional system is basically defined in the space of x and y. So, an example of a linear system can be that x dot equal to ax plus by and y dot equal to cx plus dy. So you see this is a linear system because there are no non-linear terms on the right hand side and a, b, c and d are the parameters. Now this can be written in the form of a matrix equation, right? So you can define a matrix like this: x dot equal to capital A into x, where the matrix capital X is given by the vector. So this vector basically traces is the vector of a point in the phase space at any instant of time. Right. So x is a function of t. So this vector uniquely maps a point onto this two-dimensional phase space. And the matrix capital A, this is the matrix of the parameters A, B, C, and D. So this is what any general linear system looks like. Now suppose this linear system has two solutions. Because it's a two-dimensional system, it can have two solutions, which are x1 and x2. Then any linear combination of this solution is also a solution. So we can write a general solution of the system x of t as c1 x1t plus c2 x2t. So this is a general solution for this particular system. Okay, so what is an example of physical system which we can study with, which is two-dimensional? So the simplest example is that of a linear oscillator. Mx double dot equal to k plus kx equal to 0. Now this system can be written as a system of two variables, x dot equal to v and v dot equal to minus a by m into x. Now, by the way, the fixed points of the system is basically given by the point x dot equal to 0. This gives the fixed point, which is x dot. This is the fixed point. So for this system over here, the fixed point is given by x star equal to 0 and e star equal to 0. And what does the stability of the fixed point look like? We'll come to stability later. But for the moment, what does the vector field of this system look like? So this is simply a simple harmonic oscillator. The fixed points over here. This is x and this is v. And the vector field are basically ellipses which go around like this. Okay. So this is what the vector field looks like for this particular system. So you see the fixed point at the at x comma v equal to 0 over here is actually a center. It is neither an attracting fixed point nor it is a repelling one. It is a neutrally stable fixed point. So this brings us to the concept of stability of fixed points in subsystems. So one thing which we had not seen in previous systems, which can, and the definition which now is important, is the concept of Lyapunov stability. So we call a fixed point x star as Lyapunov stable if all the trajectories which start sufficiently close to that fixed point stay near that fixed point forever. For example, the fixed point over here is a Lyapunov stable fixed point because every trajectory which starts near this fixed point always stays close to it. It's not attracted to this fixed point, but it does not also get repelled away from it. So an important thing is that Lyapunov stability does not mean exact stability. It can be a neutral stable also. Similarly, a completely stable fixed point is also not may not be Lyapunov stable because it can have unstable manifolds which can drive the system away. So we call a fixed point as a stable fixed point if it is both Lyapunov stable and it is also an attracting fixed point. And a fixed point is not Lyapunov stable or not attracting if the fixed point is neither attracting nor Lyapunov stable, it is unstable. And the example of a fixed point which is a stable fixed point but not Lyapunov stable is the flow on a circle which we had seen before. So if we have a semi-stable fixed point like this, then any slight perturbation above this fixed point will make the trajectory go around the circle and come to this fixed point. So since this kind of perturbation drives the trajectory away from the fixed point, this fixed point, although it is stable, it is not a Lyapunov stable fixed point. Okay, now we try to classify the various fixed points of a linear system. So we had seen before that linear systems can, if you have a two-dimensional linear systems, then you can have two independent solutions of the system, and all these independent solutions can be combined together to give us the total solution. Okay, so in other words, this means that we have to basically solve we had the matrix equation over here. We have to basically solve the eigenvalue equation for this matrix. We have to find the eigenvalues and the corresponding eigenvectors. So the eigenvectors will basically, since it's a two-dimensional system, if we'll get two eigenvectors. In most of the cases, there are a few exceptions where one does not exist. But in most cases, we get two eigenvectors, and two eigenvectors are sufficient to form the basis vectors which span the whole of the two-dimensional space. So that's what we'll do. So the idea of studying, of analyzing the stability of linear 2D systems is as follows. One, solve the eigenvalue equation. Second is find the eigenvectors. And finally, the third is that any linear combination uh, okay. So I think the screen sharing had stopped. So I won't write the steps again, but the third step. So the third step is that we have, if you form a linear combination of these eigenvectors, then you can get the solution of the whole system. And how do we classify whether these fixed points which we get are stable fixed points or unstable fixed points? So in order to do that, what we need to do is that we need to find the, we basically have to find the, you have to find the eigenvalues of this matrix equation. Now, one important thing which you will notice from this equation over here or a 2D system is that the fixed point the is always x comma y equal to 0. Why? Because for any general linear system, fixed point is given by this equation, right? So if you try to see the first equation, it becomes say x by b. If you substitute this in the second equation, then you get x into minus a by c equal to 0, provided that d into c is not equal to d into a. That means provided the determinant of that matrix is not equal to 0, we have the fixed point x equal to 0, which implies y equal to 0. So if the determinant of the matrix is non-zero, then one fixed point that we always have is this fixed point, which is the origin. And there are special cases that happen when the determinant is 0, which we will come to later. Okay. So therefore, the next question is that what is the stability of the fixed point? So in order to analyze stability, we have to basically find out the eigen values of the matrix. So given any particular matrix equal to A, B, C, D, suppose lambda are its eigenvalues, then the characteristic equation for the matrix basically satisfies A minus lambda into lambda minus BC equal to 0. So if you solve this equation, you will get the I2 eigenvalue is lambda. Now, a general form of the characteristic equation is as follows. That is lambda squared minus tau lambda or delta so plus delta equal to 0. Now, what is tau and delta? Tau is nothing but the trace of the matrix, say. Delta is the determinant of A. Okay. So then, if you solve this equation, the eigenvalues which one gets are lambda is equal to tau minus root over square minus or delta by 2. So these are the eigenvalues which one gets, right? So depending upon the value of tau and delta, these eigenvalues can either be positive or negative, or they can also become complex numbers if tau square becomes less than 4 delta. Okay, so this will give us a hint into the stability of the fixed point. For example, pictorially what happens is that If the eigenvalue is positive, I mean, there will be two eigenvalues of this matrix equation. All right. So if both eigenvalues are positive, then the fixed point is an unstable fixed point. If both eigenvalues are negative, then every trajectory, then both the eigendirections basically. So each eigenvalue is associated with an eigenvector, and the eigenvector basically gives us the two manifolds, which basically span the whole space. They can be stable manifolds or unstable manifolds. So a negative eigenvalue is associated with a stable manifold, and a positive eigenvalue is associated with an unstable manifold. Okay, so if both eigenvalues are negative, then both manifolds are stable, and the fixed point is an attracting fixed point or a stable fixed point. If both eigenvalues are positive, then it is an unstable fixed point since both the manifolds are unstable. If one eigenvalue is positive and the other is negative, then the fixed point is a saddle fixed point. Means there will be an attracting direction and there will be a repelling direction. That means one stable and unstable manifold. And when one eigenvalue becomes and when the eigenvalues become imaginary, become complex, then the fixed point is no longer a node. It converts into a spiral. So basically, you will have trajectories which can spiral inwards into the fixed point if it is a stable fixed point. And an inward spiral is basically classified by a negative real part of the eigenvalue. On the other hand, if the complex eigenvalue has a positive real part, it will be an unstable spiral and the trajectories will spiral outwards. And when the eigenvalues are zero, then there are special cases of stars and degenerate nodes, which we will come to gradually. Okay, so let us see how much charge I have, and accordingly, I can move ahead with this lecture. So basically, what I've been saying is that the origin is always a fixed point. So I denote the fixed point something like this. So suppose you have eigenvectors are basically vectors which characterize a line through the origin. Okay, it basically characterizes these lines which pass through fixed points. Okay, so suppose the eigendirections are like this. These are the two eigendirections, and if both the eigenvalues are negative, then it is a stable node. So this is an example of a stable node. And what does an unstable node look like? For an unstable node, both these eigendirections will be repelling outwards. So so a stable node basically means that if you have a solution coming from infinity, it will try to approach this like this. Similarly, this will try to approach it like this. And the direction of approach, it becomes it is usually parallel to the slower eigendirection. Okay, so for example, in this figure over here, as you can see, the slower eigendirection is the y direction, vertical direction, because the direction of approach is for the larger part of the trajectory parallel to the y-axis. Similarly, this is an example of a unstable node. So if you have a solution starting from here, it will go to infinity like this. A solution starting from here will again go to infinity like this, and so on and so forth. Now you can also have a saddle point where suppose these are the stable and unstable manifolds. So suppose this is the attracting manifold and this is the repelling manifold, then the trajectories will go like that. Okay. So this is an example of a saddle fixed point. In a similar manner, one can also have what I said earlier. So this happens when both the eigenvalues lambda1 and lambda2 are less than 0. This happens when lambda1 and lambda2 are greater than 0. This happens when lambda1 is greater than 0, lambda2 is less than 0, or the other way around. And finally, we can also have spirals. Spirals are basically fixed points with complex eigenvalues. So if you have an attracting spiral, the contradiction is coming like this. So this is an example of a attracting spiral, and a repelling spiral will basically have trajectories going on. This is an example of a repelling spiral. Okay, I mean, could not draw this properly, but basically the trajectory will spiral in towards these fixed points. Okay, so these were examples of spirals. So for the spirals, the eigenvectors do not exist because the eigenvectors have negative parts, and that's why they cannot be mapped onto a real plane, because the eigenvalues themselves are complex. Now this happens, a stable spiral happens when the real part of the eigenvalues. So when this happens, the real parts of both the eigenvalues are equal and they come in complex conjugate pairs. Okay. So a stable spiral happens when the real part of lambda is less than 0. And this unstable spiral happens when real part of the eigenvalue is greater than 0. And when the eigenvalues are equal, then you can have a star node. A star node basically means that you have the eigenvectors are basically degenerate eigenvectors. I mean, there can be an infinite number of eigenvectors because all eigenvalues are the same. So every vector in phase space becomes sort of like an eigenvector of the system, and therefore the rate of approach from different directions are equal. So that is what we call a star. And a degenerate node happens when one of the eigenvectors does not exist at all and there only exists one eigenvector. And this is basically the borderline case between a node and a spiral. Okay, because a spiral does not have any eigenvectors, degenerate node has one eigenvector, and the other nodes, they can have two or more eigenvectors. So we will study all these different forms of fixed points, and we will also classify them using a very convenient diagram property in the next class, and then we will look at a few examples as well. Okay, so with that, I'll stop the lecture here.